Well, good day and welcome back to the channel. This is another video. It's on batteries. It's not my typical gardening content, but it is about being self-reliant and being a person of little money, right? If you've been watching the videos, you already know that my batteries for my lawnmower gave out. So that was the start of this whole thing. I was thinking, is there a way that I can make my own battery pack? Because these are $100 a piece. And then a little bit later in July, I got the chance to sell that truck I had, which I wasn't supposed to be driving anyway, and a generator I had, and got enough money to buy an e-bike. Trouble with e-bikes is that they're made for city commuting, basically, or somebody who's just going out to the local bike park. They're not made for long distance like I have to do here. So I needed more battery power. Trouble is, the battery power that I want would cost me $2,000. So can one build their own battery cheaper than that? Well, there are some things that finding information is like pulling hen's teeth. And DIY batteries is in that list. So the last 5 months I've been researching on how to build a lithium-ion battery. And I found most of the videos, they'll show you how to put together a battery. But if you're going to go on and just watch one of those guys put together a battery and say, oh yeah, I know how to do that. So get the supplies, put it together. No. Don't. That's a very nice way to make a bomb. Lithium-ion batteries are very dangerous if they're put together wrong, but it is possible to put them together and you have a very safe battery. Just that you have to know everything. So I decided that what I would do is put together a series of videos making it a complete description of how batteries are put together, and then to build a lithium-ion battery for an e-bike, e-scooter, any of those. So to start, we're going to talk about types of batteries. I have here, I've got lead acid battery. This is a nickel cadmium. So this is the old rechargeable version that would go in your like your electric drill, battery powered electric drills. This is the newest of the, not the newest version technology of batteries, but the lightest with the most energy and the most energy dense version. It's called lithium ion. So when you're building things that you're constricted in space or weight, this is the battery that everybody is going with. This is a non-rechargeable. It's an alkaline battery, a 9-volt alkaline battery. There's two more versions of batteries. We have, you see, this one here is really explosive. If it overheats, it'll catch a fire. If you break it open, the case open, then the lithium ion ingredients inside, they can spontaneously combust. So if there's a hole in one of the battery cells, and you'll see later what I call battery cells, or if the battery cell overheats, then basically this is going to burst into flames. So they do have a lithium iron phosphate. So they make them in, they can make these into squares. Lithium iron phosphate will not combust the same way lithium ion is. It's a very safe battery. So they can put them into squares. They can make really big cells, and they can pack them right tight together. And you can make something that looks like this lead acid battery here by just packing cells together. Excellent for those battery packs when you're doing an off-grid system. So you've got your solar panels and wind generator outside, and it's recharging a battery made with these lithium iron phosphate cells. Both of these actually, and part of the reason I think why these nicocadium ran out so much is because really you should be keeping these warm. They're a little more cold tolerant than a lithium ion is, but still, they're not really that cold tolerant. You should keep them warm. Lithium ion you should keep above 5 degrees or something, 5 degrees Celsius. Alkaline, they're not rechargeable anyway. Lead acid, they're rechargeable and they're awful heavy. You can't drop this. They're easy to break. You have to put a battery together as you have to decide what voltage you want, and then you have to make the entire battery for that voltage. Now, they have come up with, and as far as I know, this is pretty much the newest technology, a lithium titanate, Titanate. That's cold tolerant. It's a solid state battery that can replace these lead acid. Now we're looking at the top of the lead acid batteries, and you see these lines. There's 1, 2, 3, and I don't know if it'd be on the camera. It might be too much shine over here, but there's a fourth one here, and a fifth one here. So there's 5 lines here. Looking at the side, you can see that line goes all the way down. Because inside this battery, it's divided. You got 5 dividers, so that makes 6 cells with acid in. Look at this, and we call it a battery. It's actually a battery cell, which serves as a battery, and I'll tell you why in a little bit. Let's pick apart the oldest version of batteries, after the lead acid that is. Now, this is a dead 9-volt battery. These are just an aluminum casing, so it's not like it's super difficult to get it apart. It just needs the right tool. Being alkaline, of course, there's never a reason really to take these apart. Unless you're trying to explain something like I'm doing here. You see, I can put my fingers right across a alkaline battery. If you did that with a lithium ion battery, you'd get a shocking experience. So, here we go. That was just the outside case. Now I've got a little, kind of a little plastic thing here. Okay, I'll keep it in there, but we've got a little piece of tin here that was spot welded onto the bottom and brought up around to the top. So this top end, you see on the battery, it was sitting here, and this was the negative and this is the positive. So this top end is a positive. But if you look at the battery, you see each divider. I've got 1, 2, 3, 4, 5, 6 cells. So we've got 6 cells in the lead acid one, 12 volt lead acid. We have 6 cells in the 9 volt alkaline. This is an 18 volt NiCad, and the case on these are put together with screws. Now we've got that taken apart. I think what I need to do is turn it upside down and take it off like this. Ooh, this one's done up better. I picked one of these apart before, and it didn't have all this wrapping on it. So this is a more later version. So the older ones didn't have this as much. That's not metal, that's just a protecting plate. But at any rate, I don't want to take this apart right now. But what I want to show is that, see this here, this is one cell. But I have 1, 2, 3, 4, 5, and they're kind of these here 5 here, and then offset 5 there. So there's 15 cells, NiCad cells, in this 18-volt battery. And now we'll open this one, the lithium ion. This is 20 volts. And so you can see that it has 5 and 5 cells. There's 10 cells in this 20-volt battery. But there's 2 are facing this way. You've got the negative, positive end this side, the negative end down that side. The positive end up this side and the negative end down this side. And then this next one is switched. And switched so they're each 2 has a strip going across, positive to positive and negative to negative, positive, negative to negative and positive to positive, and so on. So, what we seen was that this is actually a battery. This is a battery cell. And most batteries are made up of 2 or more of battery cells. Why is that? Well, I can make a lead acid battery. It's basically a container of acid, and it has one metal on one side and another metal on the other side. I can put a lot of energy into that battery, that cell. I can make it the size of a swimming pool, and I could store a whack of energy into that. But I'll only get it out at a certain voltage. Now, I got them written down. I got to take this out so I can tell you. Yeah. So our NiCad battery. This actually packs in quite a bit of energy into a small space, but it only gives me the energy of at 1.2 volts. What do I do if I want a 9 volt, right? I can, because this is not flammable, I can make a huge battery cell and store a whole bunch of energy. But still, I'd only get 1.2 volts. For the alkaline battery, that's this one that we picked apart. Regardless of how big I make that battery cell, I'm only going to get 1.5 volts. Lead acid, I'll get 2 volts per cell. Lithium titanate, I'll get 2.4 volts. Lithium iron phosphate, I'll get 3.2 volts. And the lithium ion, I'll get 3.7 volts. What happens if I want more? Now, I said this was a battery and also a battery cell because alkaline, so if I wanted a battery that was only 1.5 volts, well, with alkaline I can do it in just one cell, right? If I wanted 1.5 volts, I'd have to go with alkaline because the lithium ion, even if I made them the same size, that would give me 3.7 volts. So this is a battery cell that's also a battery. So what do I do if I want, my bike is 48 volts, right? Well, I can only get power out of this at 3.7 volts. But if I put the positive and the negative together, like that, and then I put a load between this positive and this negative, then what's going to happen is 3.7 volts is going to be forced up into this battery, this cell, and so coming out this end will be 3.7 volts from this battery plus the 3.7 from this battery, this cell, which will give me 7.4 volts. And then if I add another one on, then I've got, that'd be 11.1 volts if I put 3 together. If I stack 13 of these up, that'll add up to 48 volts, 48.1 volts or something or other. And that is going from positive to negative. Positive on one cell to the negative of the second cell. And then you go positive of the second cell to the negative of the third cell, positive of the third cell to the negative of the fourth cell, and so on. That's called linking them in series. As I said, you can just make bigger cells and you can get more energy into a cell, but these things combust. They have managed to squeeze 3.5 amp hours into a battery this size. They started out with very low ones. You can get them as low as 1.8 amp hours, I think, and higher up it goes. The reason for having lower amp hours per cell is because then the chemicals inside are not so compressed and it can let out the energy at a faster rate. This cell will only give me energy at 8 amp hours maximum. that is. Whereas a 1800 amp 1.8 amp hour battery can give me the energy at a rate of 20 amps. So it depends on, like, if you need to put something in a small space and there's not a lot of energy you need, you just need it fast, then you get the lower amp hour batteries, so you can get that energy out fast. But if you want a lot of energy and you don't have to get it out fast, then you go for the highest amp hours you can and sacrifice the speed at which you can actually pull it out. That's all well and good, but if I put these together in series, so there's 3.5 amp hours in this. If I put these together in series, I've got 3.5 amp hours at 3.7 volts. Then I do this, I'll get 3.5 amp hours at 7.4 volts. And 3.5 amp hours at 11.1 volts. The total energy is volts times amp hours, so it's the same thing. I'm getting out the same amount of energy, just at a higher voltage. So what do I do if I want to get energy longer than just the 3.5 amp hours? So what this is that I can draw energy out of this battery at 3.5 amps for 1 hour. Okay? But what if I want 14 amps at 1 hour? Well, let's see. If we put, so let's say I got 6 batteries. Okay? So that just takes out 6 battery cells. And if I were to lay them all out, in a line like this, I'd get, if I put a load between those, 22.2 volts. I'd only get 3.5 amp hours. But if I were to put them along in a line like this, so if I took a piece of metal and spot welded it on across here, all these are positive, and I did the same thing to the bottom, what I would have would be, I've got 3.5 amps maximum flowing into the metal strip here. I've got 3.5 amps flowing into it here, another 3.5 amps here, and so on. For a total of 21 amp hours that's flowing into this strip. So I can pull out off this end 21 amp hours from this piece of thing that I would have set up here. So I got a piece of metal on top, piece of metal on the bottom, and then your load would be in between on the one end, right? So that's what they call putting them in parallel. So I got 21 amp hours, but I've only got 3.7 volts. So now, if I make another set like that, exactly the same, so exactly the same set, and I'd have the metal piece across the top and bottom, but then I'd turn this set over. Okay, so I'd have a metal strip here and a metal strip here, and then I'd join them together. I'd have metal strips going across. So now I've got my parallel set here. The positive is joined to the negative. So actually it'd be like Same as if I did that. So I got 21 amp hours at 3.7 volts, 21 amp hours at 3.7 volts. Add them together, I've got 21 amp hours at 7.4 volts. Once again, if I put 6 of these along, so I'd have 21 amp hours if I put 6 of these along at 22.2 volts. Well, that of course would stretch it out. I mean, can you imagine if I got to go to 48 volts, I'd have to put 13 of these along in a line. So what we do instead is actually stand them up so we'd have all our parallel sets stood up like this, and then we'd join this positive to this negative, and then the load then would go across. They wouldn't be joined down at the bottom. The load would go between the negative here and the positive here, which is what we've seen in this. So in this battery we had 5 batteries, 10 batteries, but what we had was like that. So we had a strip across here, and here, and here, and here, and here. Now on the one side, we joined these, skipped, joined these, and then skipped. But on the other side, we joined these two, skipped, joined these two, and skipped. So then the power we've got, because we've got our 2 in parallel, we have 7 amps, and the power then will go up here, across to join here, down that battery, across to join, up this battery, across to join, down that battery, across to join, and up this one, giving us 5 in parallel, which 5 in parallel is 18.5 volts. So they rounded it up to 20 volts actually. So it's actually 18.5, so it's above 18. And when these are fully charged, then they're higher. That's the nominal voltage. So what I mean by that is that if you charge this thing fully and it goes up to 4.2 volts or something, and when it's half discharged it will be 3.7 volts. So half your time you'll be pulling at above 3.7 volts, and half the capacity you'll be pulling below 3.7 volts. So this is why they can put in this, and it's not technically 20 volts, but they can call it 20 volts because when you get it fully charged, 4.2 volts, that's 21 volts. So let's say now I've got 21 battery cells here. I put them in 7 in parallel, 3 sets of them. So I got positive up, the negative up, the positive up. That 7 in parallel is going to give me 24.5 amp hours. And putting them, joining this these two here, and then joining the 2 down here, would give me a 12 volt battery. 3 times 3.7 is, so it's a 11.1 volts, putting them in parallel, in 3 in series. Okay, I could do that, or almost enough, so I've got to add a couple. So I've got them put together like that. Now I've got 8 in series going down this way, which gives me exactly 24 volts. And I've got 3 in parallel, which will give me 10.5 amp hours. So now for about the same amount of cells, I've got one was a 12 volt 24.5 amp hours, or 24 volt with 10.5 amp hours. I could now I've got 12 in series, 2 in parallel. That'll be a 12S2P battery. That'll give me 44.4 volts with 7 amp hours, same number of battery cells. So for the bike, of course, now I'd have to add on 2 more batteries. If I made a battery like this for my bike, then I'd have a 48 volt and 7 amp hour battery. So to recap, each battery technology will give us only a certain voltage. It doesn't matter how big we make the size of the cell, it will only give a certain voltage. Lead acid, very corrosive. Lithium ion is very flammable. So they can only make the cells up to a certain size, else it gets really dangerous. Lead acid, well, it'll be heavy, and if it breaks open, you've got a whole pile of acid on to deal with. They make them 18650, so they're 18 millimeters wide, these batteries are, and 65 millimeters long. So they packed as much energy into this as they could. That is 3.5 amp hours. If you're online looking for battery cells, it will say milliamp hours, so you'll get something like 3500 milliamps. If it says it's 18650 and it's more than 3500 milliamps, they're lying to you. Don't buy it. However, so that's as much energy as they can pack into this size. They made them a little bigger. 21700. They're 21 millimeters wide and 70 millimeters long. Lithium ion. You can get those up to 5 amp hours or 5000 milliamps. You go beyond that, because of the flammability of these, you make the cell very big and you're just making a bomb. That you don't want to make a bomb. So out with the lithium iron phosphate, where they can make there is a cylinder cell. The only one I come across was the 32. It's 32 millimeters wide. I can't remember. I think it's like 41 millimeters long or something. It's a fairly large cell. But then they went to the square ones so they could pack them all in. So there's 2 reasons for restricting the size. One is you have to get the voltage, so you have to have so many cells. And with this, well, the bigger the cell, the more dangerous. That's the first part, just the lowdown on why a battery is made up of several cells rather than being just this one big block of material. And I hope you found it interesting. Canada Post is on strike, so I've got to wait for a few parts that it's all in Canada, all cleared customs, but it's sitting there waiting for Canada Post to go back to work. Then I can continue with the building of this battery, and I'll show you and explain each part as we go along. Thanks for watching, and I'll see you in the next one.